My name is Tariq Javed, and welcome to my presentation about evolution in test requirements of an embedded system. Here, I would like to give you an overview of ever-changing technology landscape within the automotive industry, and as a test community, continuous struggle to find the best methods and best solution to test the embedded systems. Now, this is our typical, very simple embedded system where we've got the application, we've got the embedded software in the middle, and then we've got the we would have the hardware at the bottom. Now, hardware micro is chosen based on the specifications or requirements of a function of that ECU, and then the application would be written keeping in mind the constraints and capabilities of that hardware. Now, that application together with the embedded software is knitted together to work on that hardware. The software and hardware are very much dependent on each other. Now, we are, as an industry, moving towards much more dynamic setup where we would like to make the software independent of the hardware. So to be able to host any application software on any given hardware, as well as hosting many more applications on a single hardware setup. As from the testing point of view, this is our system under test, where we'll have some inputs and then we'll have the outputs on the other side. We would like to manipulate the inputs to be able to test the actual function of this system under test, and we will verify it by looking at the outputs whether it passes that criteria or not. Now, purely for understanding and analysis point of view, I have divided all the development right up until now and in the future into 3 different phases. First phase, running up to 99, I've classed it as the mechatronic. Mechatronic phase, where the emphasis was more on the mechanical, on the physical parts. We started to see some communication protocol making its way into the car. The second phase runs from 2000 up until now, of 20 years. Here, the focus shifted towards more electrical and electronic systems. Importance or emphasis on the electronic and electrical systems increased, and that's where we started to see many more communication protocols making their way into the car. And then the future is all about the software. Future is all about the artificial intelligence, and that's where we would see completely autonomous vehicle in the future. I've seen announcements by one of the leading German auto manufacturer that the level 3 autonomous car would become available around this time, as well as Tesla owner Elon Musk made an announcement that the level 5 autonomous car would be available, or would become available even this year, which I think is quite ambitious, but we'll see how it pans out. Now, let's discuss this mechatronic phase in a bit more detail. Now, this is the phase where we started to see these electronic systems making their way into the car. So if we look in a bit more detail, these are kind of the core functions which would keep the car going, obviously. On the powertrain side, obviously, the engine control units, ABS, transmission, and then on the body electronic side, body control module, door module, and seat modules were developed and introduced into the car. This is the era when we shifted from point-to-point connections to introducing first a communication protocol as CAN bus. So CAN bus was introduced in the early 90s into the cars, and towards the end of the 90s, more and more manufacturers started to introduce CAN bus into the cars. Now, looking at it from the testing point of view, like I said, this was the time when the car manufacturers were still positioned as the mechanical companies. So getting the physical mechanical parts right was the big focus. So this is a typical example of a test setup where if you are testing a seat, door, even steering column or lighting, you would have this kind of setup where you'll have sensors, actuators, and then you'll have the data acquisition. And then, of course, you'll have the CAN inputs or other analog digital inputs to the ECU. So ECU would be there, obviously, but the focus wouldn't be on this electronic control unit. Rather, the focus would be getting the physical endurance test as well as life cycle test done. As well as this type of test, we probably saw EMC testing done. Make sure that the stereo or radio you're using, your signals are not getting affected. As well as other types of testing, which were in the focus was making sure that the car would function okay in the hot or cold climate. Then there was a paradigm shift as we moved into the 2000, running up to 2020 now. Here the focus shifted more on the electronics systems. So getting the electronic system right started to increase, as well as advancements in the powertrain electronics. The systems which were introduced previously, as well as the body electronic systems, we started to see more and more functions which were more linked to comfort and the convenience started to appear. So here we see, if you see the correlation between these functions, these are all the ADAS based systems. These systems started to make way into the car. Now, all of these systems, a lot of software, a lot of electronics, pushed for more bandwidth, and that's why we started to see a lot of other communication protocols appearing within the car. So we saw FlexRay, we saw MOST, we saw many more CAN buses introduced within the car, as well as we saw the LIN. So LIN obviously was there to address the low bandwidth requirements where CAN was deemed too expensive. Now, from the testing methods point of view, we saw the focus on the mill, hill, and sill, which we will discuss now. So, one of the testing technique which was on the focus was getting more and more automation and more reusability of the tests to achieve higher efficiency. We have seen a lot of automation or more automation within the companies, but we could of course do with more automation. Then we saw more unit testing. So as the focus is shifting more onto the software, we started to see more safety requirements appearing on the embedded systems. Testing the source code is becoming indispensable. So thus the unit testing is on the rise. And then comes the actual software development, shift in the software development. So previously you would hand code the software in embedded C, but we started to see more and more software developed with the modeling. So you would model the software. So since with this technique, the byproduct was obviously that the model was available. Obviously, people started to use this model for the testing purposes. So the technique appeared was the mill, model in loop. So once the model is ready, then you could take this model in the virtual environment and you could start testing. Second step would be that you would generate the code from this model, and then you would repeat the same test on this software. That would be called SIL, software in loop. And the third step, obvious step, would be that once that software together with the embedded software is then deployed on the actual hardware, then that is our system under test. That is the actual system which is going to get into the car. So testing that in a controlled fashion, that's where we have the hill test bench. So here, for example, I'll show you how the typical hill test bench would look like. So you would have a typical control software with the complete Russell bus simulation setup. You would design your test cases, of course, within the VTest Studio, and then you would interface with the environment modeling software and the physical modeling software. So you have a complete virtual environment to carry out this testing. And then system under test would then be connected to the hill setup, connecting to the inputs and outputs of the system, and then of course controlling this system under test with whichever bus systems is being that system under test is using. So you would utilize that type of interface, obviously, to connect and control the system under test. Another important step we saw was managing all of these all of this process. So the test management became very important, managing the test requirements, of course, and then running the test and getting the results. So getting a complete traceability of the test results and linking them to the actual test cases, and then linking the test cases to the actual test requirements has become very beneficial, and people started to see a lot of value in doing and managing the whole test process this way. Then another aspect which I wanted to address separately was the Ethernet. So Ethernet has started to make its way into the car. So we started to see more and more Ethernet development from 2012 onwards. If we look at the OSI model here, so base, two layers, PHY and the MAC layer, this is what we would call it as the automotive Ethernet. So we have two physical layers, 100 base T1 and 1000 base T1 already in the development, and about 3 or 4 other different physical layers are going through the standardization process. So we already have within the Ethernet, we have more physical layers we are dealing with than all the physical layers we have come across up until now, combined from the other communication protocols. So here we have many more challenges of testing those physical layers and getting those physical layers right to be deployed within the car. Then obviously we are getting used to of the whole TCP/IP concept. Getting this right is also very very important. And then the actual application layer protocols, which are more automotive specific, such as the some IP, do IP, and then the applications which would be more time sensitive, obviously, would then utilize the TCN functionality. Now, if we look at what's going to be the automotive trends which would drive the innovation in the future, here we see the connectivity. So connecting to the external world, so connecting to any external applications, whether it is the third party or whether it is the OEM's own backend for software uploads. That's going to be a very, very important area. Other than that, the autonomous, I already mentioned, that's going to be a very focal point for almost every company. We'll see a lot of improvements and innovations in the sensor, lidar, radars, and cameras technologies. We would see a lot more bandwidth requirements and computing resource requirements, of course, in the future. E-mobility, that's another important drivers for the future development, of course, to achieve energy efficiency, of course, and getting achieving the battery optimization, as well as the V2X technology, which has been around for a few years, obviously, but I think as we move more towards the autonomous vehicles, obviously, the V2X will gain its importance, and this, of course, will give us more traffic safety and efficiency, and of course, it will improve the environment. One other factor which I would like to mention, and this is something very much a driver from this year, is the remote working. So all of us, the whole world, obviously, the automotive world, and as a test community, we are getting used to working from home. We are getting used to of not having access to the test equipment all the time. And that's the new norm, obviously. So people are coming up with different ways of accessing the test hardware and obviously carrying out the remote testing. And that is something which is not going to go away, and that is something we're going to have to get used to of more and more. Now, if we look at the architecture going into the future of a car, so here, if I can explain three different layers of the architecture. So the green blocks you see here, these are the standard ECUs, the embedded system ECUs we are familiar with. These would utilize the AutoSAR Classic as they are using now based on the static configurations. These will communicate over the CAN, LIN, and FlexRay, and very much signal oriented. Then the layer 2 and 3, which is what the domain controller and the central computing ECU would be. These are the systems which would utilize the AutoSAR adaptive. This is where the third-party applications would be hosted. All the communications would be done on the Ethernet, and the communications would utilize the service-oriented communication method. Now, from the testing point of view, if we take into account these three different layers and how we're going to address the testing. So the base layer, the layer 1, as I mentioned, consists of the conventional ECUs. These are the smart sensors and the actuators. We would do testing probably same way as we've been doing, as we've been testing these embedded systems. So utilizing the mail, cell, and HEL setups would carry on for these ECUs. The challenge would be for this middle layer, the layer 2. That's where we're going to be testing the domain controllers and central computing units. Now here, we have a challenge of dealing with highly complex ADAS functions, which would mean huge amount of test scenarios to deal with. As well as, I've seen a figure of about 100 million kilometers or miles of testing to be done for autonomous car to become accepted. That is a huge number. If we think of doing this test mileage on the road, that will be almost impossible. So we'll have to think of how we can virtualize it. So part of it is done virtually within the test environment, and then part of it, of course, on the road in the car. as well as integration of these several applications, as I mentioned. So here we are dealing with the service-oriented architecture, which obviously gives us this flexibility that we can host more applications. So we have to start dealing, and we have to think of how we can test any applications which is then once it is deployed, how well it would work within that environment, as well as making use of the continuous integration and server testing. That is a new those are the new techniques which you'll have to get used to. Now, from when you think of the test tool, we'll have to think of few requirements. First of all, we'll have to think of how we can virtualize our system under test. That's the very first thing. Second thing, we'll have to think of whether the test tool can support the continuous integration integration methods, because there'll be teams developing software within the OEMs as well as the tier ones, and then there'll be a lot of builds done on daily basis, hundreds of builds done on a daily basis, and you would like to test those builds as soon as those builds are finished. So you like to pick a tool which can carry out the testing of those builds in hundreds, as well as being able to initiate number of instances of this software. So that's where we are introducing a product which is just another variant of Canoe for server. So Canoe for server is the tool which is based on obviously the Canoe, and with, for example, with the Jenkins software, you could initiate hundreds of instances of the software within the Linux server, or for that matter within the Windows server, and then obviously you will be able to collect the results at the end in the report form. Then comes to the layer 3. So layer 3, as I mentioned, is connectivity, connection to the backend server of the OEM, or connection to the internet and web. Now here we'll have to think of how can we test those applications which are running within the OEM backend or other servers. So the focus, keeping in mind here, wouldn't be the connectivity. So we'll have to take the connection as it is. It could be the Wi-Fi, 4G, or moving into the future 5G. The focus here would be testing the applications which would be running within the backend. So if I take example here, I'll try to explain it to you. So we've got the central locking model as a software component hosted, simulated within the Canoe environment. Canoe would also have the testing scenario to test this, and then Canoe for software would be connected using the MQTT protocol over the CFS backend to the customer cloud. So customer cloud will host the applications, which would check the legitimacy of the requests coming from the user, obviously, and then would issue the commands to the target software component to carry out that task. So here, for example, Canoe, from the Canoe, the test could be that we would like to unlock the car, so the request would then go over the CFS backend into the customer cloud. The application would verify it, and then obviously would send the command back to the this simulated software model within the Canoe to carry out this unlocking. Software here, in this case, this model is simulated within the Canoe environment, but Second step could be that it is actually deployed within the car, and only the testing or the test scenario is hosted within the kennel. So that's how those applications would be tested. Now, just to summarize all of this, as we've discussed, and we would carry on seeing more and more complex ADAS features appearing within the car. So we'll have to think of how we can test these new systems. Now, designing the safety critical system is a big challenge, but I think testing that system is even bigger challenge. If that wasn't enough, then we'll have to also deal with the service-oriented architecture-based systems with high dynamic nature in the future. Remote working, which I highlighted earlier, is something we'll have to deal with. This is something we have started to experience only this year with remote and lively access to the test equipment. And then the concepts of continuous integration, as well as the testing within the server. So these are not the new concepts. People in the development are familiar with, software engineers are familiar with, but within the testing community, these are the new concepts. So we'll have to get used to of it and make best use of these concepts. Thank you very much.